very much again. Thanks. Can you hear, right? Thank you very much again for having me here. It's an honor and privilege to be speaking to this esteemed audience. Two things. First of all, I have shared my slide with the organizers half an hour before Dr. Chaudhary presented the beautiful thing. So there is a lot of things in common. Please don't think that I am copying from him, because his was a wonderful speech. I learned so much there. There is so much of material in common. We will just touch upon the practical aspects, the AI standpoint did. And thank you, Dr. Chaudhary, again for the wonderful word of caution that yes, we should celebrate AI, but there are a few things we have to be also careful about. It's a fantastic talk. Yeah. This is okay. I'll if you have a little like that. Hello. You can hear me, right? Okay. Okay. This is okay? All right. So, so very quickly, and I have with me Vinod Kumar. He is the head of energy. Vinod, can you come on the stage, please? So we have half an hour, 15-20 minutes. We'll talk about AI. Then we will go through a very specific use case, a couple of use cases actually that we have been working on, and some of the interesting things here. So very quickly, the agenda out here. So here is Vinod Kumar. Yes, a round of applause. So thank you again. So let's get into the thing. So artificial intelligence, technology, techniques, and trends. I will lightly touch upon it. It's such a vast subject, and we all already heard some of the very key concepts. But I will try to share some of the way we look at it, at transformer architecture and the generative AI and stuff like that. Very quickly, you see, last afternoon when I was preparing these slides, what I did was, you heard about Vision LLM. So I went to ChatGPT and said, can you generate me a power plant in the Indian context? What are the key things? Can you share with me what would be the blueprint? And this is what it came up with. Now, I am not an electrical engineer. I am not a power system specialist. But I can tell you one thing. Some of the things, the way it captures the universe of knowledge and it tries to present to you, it amazes me. It's very impressive. Of course, there are problems. One of the big problems, hallucination. We'll talk about that in a minute. But the big thing about this generative AI, the general artificial intelligence, AGI, they were calling about it in Davos just a few weeks back, big time. It's really transformative. Now, let's get into, so you can take a look at this slide and see like what are the really, it's doing something useful, but let's get into a computation. Now here, this is an important slide. Now when I say old world and a new world, it does not mean that old is bad and actually they are truly old. But the interesting things that we are seeing in the world that we were living in, it was more human-centric, thought-intensive. The world that is coming up, it's more computation-intensive. Now, do we need a human in the loop today? Absolutely yes. No question about it. because many of these AI systems on their own, you cannot fully trust them. But the work is going on here in Hitachi R&D, in my previous organization, IBM, every day on the floor. How can we go and make it more bias-free, more ethical, more accurate? And this has been a journey I'm seeing right from 2009, 2010, when AI was coming back, and those days IBM Watson was taking a big lead worldwide. So I used to sell wealth management solutions to the banks, some of the predictive maintenance solutions that you heard about today for the manufacturing companies, insurance companies, the car. You take the picture of the car, and then there is a bright sunlight shining on the metal of the car. How do you take that effect off and try to understand what damage has been done to the car? And based on that, you come up with an automated estimate right then and there where the accident happened. There was a company here called Tokyo Marine, very famous company. They're headquartered in Ifko Chowk in Delhi. And in 2012-13, we have been working with them on such kind of things. However, something is changing. Something has changed big time. And one of the key watershed moments of that change is a wonderful paper in 2017 by a gentleman, Ashish Vaswani and the group from Google. And that's the basis of the transformer architecture that Dr. Chaudhary was so nicely presenting, and we will talk about that. So some of the things that we were doing between 2009 and 2016-17, a lot of them were, of course, a lot on the natural language processing side, but analytics, clustering, segmentation, K-means clustering, those were the things that were very, very popular at that time. We'll go to a large marketing agency like AC Nielsen and all, and suddenly we'll say Dun and Humby. They will give us a whole bunch of data, and our first thing was, how can you segment the data, micro segments, and you can offer promotions. And the kind of techniques those days, many techniques, like in case of credit card analytics and all, shade analysis, cart analysis, CR5, clustering, segmentation, those were the things we were doing those days. In 2017, 18, 19 onwards, it is more and more we are seeing the two things. You heard about discriminative AI, and now it is more and more of generative AI. Now, when I say again the old world and the new world, old world can again be new, right? I mean, you know, everything changes, including the fashion world, our societal changes, almost everything is repetitive, though probably in a spiral, not really in a circular motion. Now, if you look, the world that we have been living between 1985, 90s, 2000, a lot of them were rules driven. You have certain rules and credit card, or for example, for your banking transaction, you take 10 rupees and you debit 10 rupees. It's a very, very deterministic computing. And deterministic computing is still very important. There are many mission critical operations like nuclear power plants, 3 Mile Island. There, you just cannot go and come up with another probabilistic model like the way we are doing in AI today. Because if you do so, you have to have basically 100%, otherwise people will die. So deterministic things still very important. But more and more we are seeing probabilistic things. Google search is a wonderful example. Friday evening you are going out, you look for a Chinese restaurant nearby, and whatever Chinese restaurant you come up with, the top 3 probably is one of the things that satisfies your case. It does not have to be right on the spot, that 10 rupees plus minus, not 9.999 or 10.111, and you are happy with that. Why is this probabilistic world so popular today? And it is not so popular, it's gaining prominence because of 2 reasons. And we'll talk about that. One is, of course, the computation has become cheaper, and there is so much amount of data out there world, and you don't have time to go through and create rules out of all of them. But if you have a scalable AI model running somewhere and you tell me something with a reasonably good amount of accuracy, probably I'm happy. And of course, this is not a world where we can live in all the time. But majority of the times, this probabilistic world is winning over. Second, if you look at classical statistics, when we used to have an hypothesis, and this is still very important in pharmaceutical world today, you go to pharmaceuticals, you go with a hypothesis that this drug is really good. It cures your headache or it cures your disease. There, still they have a hypothesis, they test the hypothesis, all kind of thing, t-test, chi-square and all that thing, and you come up with an answer. Okay, hypothesis rejected, 95% confidence interval. It is not going to work. The drug has no effect. But if you look at many other operations in this thing, the rules are being discovered. The rules are, so first of all, the hypothesis itself, you don't have any. The hypothesis is being formed, updated. This is more like data telling you something which you did not. Let me give you a fantastic example. There is a wind turbine. We have been working off the coast of UK, as well as later in Gujarat. Out here, the wind turbines were there, and it's a common operations. We, Hitachi R&D, we have been cooperating with Hitachi Europe. We have been working on a model, and they told us a physics-informed neural network model, and mainly driven by the physics laws, that if this is how the blades and all these things, the yaw, the pitch and all, this is going to happen, it will generate the maximum output. When we took that data from the ground and started developing a data-driven model, it started confronting some of the basic ideas of physics. So now we are seeing something. Obviously, the physics laws are not bad. They have been for 300, 400 years. People have been working on maths, stats, calculus, all that thing, and it's for real. You just cannot go and say no. It's still important. You know it. Yet, when in that objective condition, when we start getting the data, we start that some of those rules and formulas are not exactly how it works out. So how do you go and do the conciliation between the data-driven world and the physics world? And that's where some of the important papers in Hitachi, you can easily look it up in Google Patents, PIN, Physics Informed from Hitachi Energy, which is our power and distribution unit, the erstwhile ABB. That's what we have been working with. So it's very interesting. The rules-driven world versus rules-discovered world. Rules discovered by the data and not always by humans, trying to estimate the parameters. The machine is trying to tell you what the parameters are. That's a very interesting thing. So if you see this picture out here, the line of regression, you see, if you try to go and come up with all the coefficients of regression, whether it's a straight line or whether it's exponential and all, it does not tell you always the right story, the accurate story. Very often it is a squiggly line. It was there in Dr. Chaudhary's presentation. There was a line like this. How do you go and achieve such non-linearity? And this is where the neural networks are very, very powerful, because they have billions of parameters between the input and the output, which means you have billions of levers. You can take this up, bring the weight down, add some bias. You can do all kinds of things, billion different combinations, trillions of combinations, right? Billion parameters, billion into billion. You do the math, the order. And with that many possibilities, now your ability to achieve the squiggly line, exactly taking the blue one out here, but dipping down, taking the red out, that kind of segmentation, now neural network does. What is the problem then? The problem is, of course, neural networks and all these things, deep learning, they are usually much more accurate. We have seen that. But you cannot explain it to always. You cannot go and explain it to somebody who is investing in their wealth management fund or pension fund. their entire life savings to something, and you cannot explain them because you say, oh, my neural network model, billion parameters told me that. No, 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 no. They want to hear something very simple. Is this fund giving me a return for last 3 years as high as, is this fund being run by people who really understand it? Same thing with pharmaceuticals. People want to say, you have done 10 experiments, it has 3 people, what are the adverse reactions? And a lot of things they will ask. So you have got to explain what this machine learning neural network thinks. This is called a very interesting area called explainable AI. How can you explain it in terms of human understanding? Some few parameters that humans can absorb. Humans cannot absorb all those nameless, meaningless billion parameters out of them. So this is the interesting aspect of neural network. So if you look, it is not about estimation. Here also we do estimation of parameters, but the machine is doing it in the new world, and it's a much larger number of parameters, and there are all kinds of algorithms, backpropagation and all that technique that we do. Now what does that mean? And of course this is a more Bayesian world. You take a first of all, you may not have any hypothesis, and even if you have a hypothesis, you are having the data update your hypothesis real time. If you look at reinforcement learning, at the end of the day, reinforcement learning is either giving you a reward or a penalty because of which you are going down that path or this path. So every time you are iterating, you are, that's why in a company like Hitachi, we are saying that let us do fail fast. Let us do something, fail quickly, understand from it, and from the iteration we move forward. As opposed to doing it the very right, correct, the meticulous Japanese way we have always been doing our business for last 100 years. That's very good, but that's waterfall approach. By the time you go and you do it, all the technology has moved on. So this is a very interesting thought. So you see, I told you about so many levers that you have between the new world, that blue picture you see, the input and the output. Between the two worlds, there are so many parameters, and this discretization of the problem into small little fragments, which are all configurable and configured by the machine. That's exactly what the new world deep learning is. Now, if I look at some of the interesting things, you have this whole world of AI, and then you have the machine learning world, then you have the deep learning world, and now one big problem of deep learning is the problem of grounding that Dr. Chaudhary was saying, that it doesn't understand what really red means. It knows red by association. Now, there are two schools of thought. There are two things in deep learning, by the way. If you go and read up, if you listen to Yvonne Lachun and Jan Lachun and some of these people, you will see that they are really talking about what deep learning today, that is not really reflecting the perception, the real thing that's happening in the world. That grounding is not there. But then there are also people like us who are practicing it every day and trying to make million parameters to billion parameters, billion parameters to trillion parameters, and trying to see what we can achieve with the existing model. Can it become better? But these are active areas of research. Now, two things. You heard about unsupervised learning and supervised. The world moves between the two very interestingly. In 2013, when we were doing k-means clustering and all that thing, we will give all the data to that algorithm and tell, hey, you know what? Go and cluster yourself. Find out who are you naturally akin to, alike with, and accordingly be in that group. Today, then, came the discriminative AI, where people have been annotating and telling, oh, you are cat, you are dog, you are cat, you are dog. And after 10,000 such images, you give an image and says, okay, I have learned from you what is a cat and dog. You taught me. So basically, you have supervised my understanding and learning, and hence, I will be able to tell you the better. So the supervised learning was trumping around 2016, 17, 18. And then this generative AI came. And again, we are going back a little bit to the unsupervised or semi-supervised world, where we will tell you This is the most interesting thing. This is how we do it. Generative AI, key disruptor. I can't tell you how much of R&D research dollars. Hitachi is a $80 billion company. It is not about air conditioners. We do a lot of stuff. We do bullet trains, Shinkansen in Japan. We do Hitachi Energy, the power transmission, 70-80% of the transmission line here in India that has got Hitachi footprint there, right? It has got 800 kilovolt transmission line from Raigad to a place in Tamil Nadu, far south, but thousands of miles it is doing all that power transmission. So we do a lot of things. We do space tech, but out of that 880 billion, $4 billion we spend in R&D. And out of that $4 billion, at least $500 million was invested only in understanding generative AI. And this war continues today. So why are we giving so much money? So let's look at it. You heard from Dr. Chaudhary again. It was such a wonderful thing. Attention. It is about, you know, when I used to go to school many years back in South Point and all, there was a badge, there was a symbol that used to say, know thyself, Atmanang Viddhi. So you better know what you have. So in this transformer architecture, if you see out here, from here, the data, the input that is coming, it is doing something amazing. It is looking at, for example, the cat is lying on a mat, the English translation for which the French translation will come out from here. The French will come out from there. And the English sentence will come from here. And in between, while I am training, all the English sentences that go in here and all the French sentences that go in here, somewhere here, it is doing the cross attention. That is basically the cat is lying on the mat and its French equivalent, they are kind of, doing the cross correlation, cross attention, and you are trying cross association, and they are trying to find out and giving a weight to it. Why is this transformer architecture so beautiful? Because you started with a text. It took the text and turned it into numbers. And then you are doing all kinds of numbers jugglery, matrices, and all the connections. Seeing, is cat really more similar to mat? Or is it semantically very different? A mat and a cat, though maybe phonetically they are same, but they mean very different things. So let us give them some numbers very much away from each other. So if it is a director IIT Delhi, where the director is here and IIT Delhi is there, if we can go and separate them out, awesome. Then I will come to know that he is not really a director of IIT Delhi. He will be a director of IIT Guwahati. So how can we give the right numbers, the weightage to those words in that context? So once you have given all these numbers and once you have done all the jugglery with numbers, and now from the numbers you are going back to the text. This technique is very, very similar to what we heard while we do electrical engineering, Fourier transform, or for example, even the gramophones. When we have when we have the sound and the variation in the wax, the needle, to the depth it goes, it is that variation that matters. It is the variation between the words, how different they are, how close they are, the proximity and all. That's all that we are trying to encode. If we can go and encode it using whatever means, whether it is the wax means, whether it is a carrier wave, on the piggybacking on that, you are taking that variation, or it is transformer architecture, it doesn't matter. All you have to remember how you have encoded so that when it comes back, you get the transform back from the text to from the numbers back to the text world with the same scheme that you started with. It's awesome. The only thing is the whole thing that you are doing now is with data. You have data in the form of text, you have data in the form of image, you have data in the form of sound. All this data is being encoded, and then all this jugglery happening, proximity analysis happening, if I may. And there are many interesting, if you forget what was the main thing, you see all these things that are coming out here, This thing's all coming out here, back again. It is not letting you forget the original context. Again, you are bringing back the original context and reminding that computation engine, by the way, you have forgotten the original thing. Go and bring that back, understand it, remember it a little bit more. And then you do so this jumbling up and this analysis, that's the beauty. But it's nothing very earth shattering, except the fact the guys who came up with it is, and here are some AI applications, and you heard so many times one application. So you see demand supply prediction, network Hitachi Nostradamus tool. Please look up at that one. That's a beautiful tool. Asset management tool, somebody mentioned, Mr. Salwan, very interesting. Plant maintenance is one area where you can start right away today. DeepSeek is there. Alibaba's Cohen is there. You just go and download it. And then you do retraining it, or you do reinforcement learning, fine tune it, you do whatever you want to do. The code is there. All you have got to do is to download the stuff, start working on it, and there are many techniques. There is a retrieval augmented generation, a RAG approach and all. But the main thing is, you have in Kolaghat thermal power station, Bakrishra thermal power station, whole bunch of data. Go and shove it into the large language model and see what kind of results it starts coming out with. You'd be amazed that in 2012-13, with the Woodside Corporation in Australia, we have been doing plant maintenance manual for their engineers. When they will go and get the gas from the coast of Western Australia, suddenly the plant shut down, and they will take the gas and they didn't know what to do, and they will ask questions in an iPad, pretty much the chat GPT way. The only thing you realize that this retrieval, you have to make it more and more accurate, more and more situation specific, and the better it gets with all these LLMs and something very important, that is agentic AI. Sometimes you cannot do it all by yourselves by an LLM. You have got to go and take help of optimization agent. You have to take help of a quadratic programming agent, or for example some other agent. You just go and call that, and that will do all its 300 years of science and technology. It's in motion for you. It will go and come up with a more accurate answer, and that answer now you integrate it, and all this integration and calling is being done, orchestrated by something called agentic AI frameworks. There are many out there, and you can try. Okay, I will very quickly go for 5-10 minutes. If you can please share with us some very interesting work that we are doing on microgrid optimization. Here is one of the IITs here, and then with some of the power grid corporations in UK, we are working with. Very quickly, if you can take this, and it's an optimization problem. It's an agent problem that is being integrated into LLM using a agentic AI framework problem. So, Vinod, to you.
Thank you very much, Kingshuk, and thank you for giving me a chance to talk. I'll give you an example. Actually, this is a small example. It's called microgrid, as you can say, but please don't limit yourself from creatively thinking how it can be expanded to the entire grid itself. So here is a case study where you have three cases. So one of is, let me also say, because we are working with the European context, so there is the tariff changes with the time. So if you have sun at a particular time, you can do a better job at saving it in the storage, battery storage, and releasing it when the peak load is there or when the price is high. So first problem is all about cost optimization. How do you manage your energy cost by leveraging battery and predicting when the loads would be high or the sunlight would be high? The second is peak shaving, because load is growing so fast. You have data centers, you have EVs in the load side, and it is more stochastic. So how do you manage those peaks effectively using again this kind of an arrangement? Third is for more of a renewable generation companies who have to estimate day ahead, and many a times actually they exceed or don't meet the criteria. There are penalties associated. So how you can again use storage and optimization to do this. So on the right hand side, you can see the very brief kind of diagram. You call a microgrid differentiate from the grid with a point of common coupling from where you have behind the meter and all these things. So the key element of optimization is the battery energy storage. It could be any other kind of storage for that matter, and there is a forecasting involved. I'll just run you through. By the way, both of these images are also generated by AI. So this is an example of a shopping complex which is acting as a microgrid, and you have EVs in addition to the other loads coming in at particular time. So there are peaks that you can see. There is a dotted line which is all about the grid limitation, and then you have peaks, and around those peaks you have variability. So that variability is the key point actually. And when you look at in the mega grid scale, so you have a lot of variability in the loads and the congestion that the grid has. So similarly, the variability normally would give you an opportunity to reduce the cost by procuring energy at a price. But on the other hand, variability at the margins where there is limit, actually it creates another kind of a problem, which is kind of either you have to have a penalty or there is shutdown. So two kind of problems are there. Now, there's a lot of talk about the transformer. You will be amazed to know actually there are traditional ways of forecasting, the load forecasting or EV load forecasting or the renewable forecasting that have come. We have used time series, time and tested, but there are now these evolved. So transformer models, you can look up for time LLMs and things like that. They're doing a fantastic job. The accuracies are much higher, and that is a starting point for us. We use such models, but then nowhere you can reach 100% accuracy, and that is the next point actually. When you cannot reach 100% accuracy because it's a complete stochastic process, you cannot second guess when the EVs are coming in. So you have to manage the errors, and those errors are managed with the kind of optimization called stochastic optimization. So you have multiple conditions of constraints or multiple objective functions, and you try to solve all of them for various ranges of error. So that is one amazing thing actually which has happened. We do it for two settings. We do it for a setting which is more not in the border, that is a stochastic optimization, and we do it also for where it is around the border, there is robust estimation actually. And we have simulated this. We've done these experiments as Kingshuk mentioned in European use case. The work is presented in IEEE Big Data 2024. These are some of the interesting results that we have got. You have robust optimization that does a very good job of the x-axis is the violation of peaks, the y-axis is the cost optimization. So one kind of optimization will do good in terms of violation of the peaks. The other would do a good job in terms of reducing the cost. So this is the summary. But what I would like to end the note is actually energy and power systems. Actually, it is so complex. Microgrid is just a small, if you consider just few EV loads and things like that, you can manage with the traditional physics-based, formulas and the optimized mathematical models. But imagine when it grows up, the number of controllable batteries or generators are so many, and then you would need to get into the deep learning mode and the AI that we spoke about. So please be creative when you're looking up how this can go ahead. Thank you for your time.
Thank you very much. Thanks a lot.